All right, it is 8 o'clock, so we're going to go ahead and get started. Today, we're going to be talking about steady state sinusoidal circuit analysis, and I'm going to use this to review some of the exam one techniques that we've previously learned. Let's start with the following circuit. We're going to have some steady state sinusoidal voltage source Vs of t, and I'll tell you what this is momentarily. Let's have a 5 ohm resistor here, a 2 Henry inductor here, let's make this 1/3 of a farad. Let's make this 3 ohms. Another capacitor, let's make this 1/2 of a farad. And then we're going to have a steady state sinusoidal current source over here on the right. Let's call this Is of t. Let's define Vs of t to be 10 cosine 2t plus 30 degrees volts. And let's define Is of t to be 0.8 sine of 2t plus 60 degrees amps. And our ultimate goal in this particular problem will be to solve for this capacitor voltage as a function of time. So the first thing that we're going to do is convert this circuit from the time domain into the frequency domain. So I'm going to redraw my circuit. This would be a voltage source, my apologies. And then we are going to just kind of fill in values for frequency domain values for all of our components, and then frequency domain representations for all of our voltages and currents here in just a minute. So let's start with our source voltage. How do I represent that time domain function Vs of t as a phasor? 10 angle 30 degrees, right? So I keep the magnitude, keep the phase angle, throw the rest away. So 10 angle 30 degrees volts will go over here. What about my source current 0.8 sine 2t plus 60 degrees? I have to convert it to cosine first, absolutely correct. How do I do that? Subtract 90 degrees from the phase angle. So 0.8 sine 2t plus 60 degrees is the same thing as 0.8 cosine 2t minus 30 degrees. What's my phasor representation then? 0.8 angle negative 30 degrees. Absolutely right. All right. So what is the impedance of each of my resistors going to look like? Just the resistor value itself, so the resistors do not change. So that's going to be a 5 ohm resistor here and a 3 ohm resistor here. What should the impedance of my inductor look like? J omega L. Okay, so what's omega in this case? 2 radians per second. All right, so 2 radians per second times 2 henries is going to look like 4 ohms. So that we're going to have a J4 ohm impedance here for our inductor. What's the impedance of a capacitor? 1 over J omega C, or negative J divided by omega C. So for our 1/2 of a farad capacitor, so Z 1/2 of a farad is going to be negative J divided by 2 times 1/2. So that's just going to be negative J1. The impedance of our 1/3 of a farad is going to be negative J times 2 times 1/3. So that's going to be negative J over 2/3. So minus J 3/2 of a farad. And then lastly, the quantity that we're solving for converted into the frequency domain is going to be the phasor voltage VC. I don't like how that V looks like. Okay. All right, so because you guys specifically asked to have superposition, voltage division, and current division reviewed, I'm going to work this problem using superposition, voltage division, and current division. Okay. So scroll up here just a smidge, actually. So using superposition, we're going to work this problem twice. Okay. The first time I'm going to want my voltage source on and my current source off. So that's going to look like this. I have 10 angle 30 degrees volts. Five ohms, J4 ohms, minus J 3/2 of an ohm, over which I'm going to have my voltage VC prime. Three ohms minus J1 ohms. Like so. I'm going to solve for the voltage VC prime using voltage division. So VC prime is going to be given by my voltage, 10 angle 30 degrees volts. In the numerator, I'm going to have the impedance I'm trying to find the voltage drop over. So that's going to look like negative J times 3/2 of an ohm. In the denominator, I'm going to have the series impedance seen by that voltage source. So I first see a total impedance of 5 plus J4 ohms. And then I add to that negative J 3/2 of an ohm. Okay. So really what I'm doing here, and it doesn't particularly matter, but it's a good habit to do, is I'm lumping these two guys together as a single equivalent impedance that is just 5 plus J4 ohms overall, right? The reason why I tend to do that is because it effectively eliminates a node if we were going to try to apply KCL or anything like that, right? We can lump all of that together as a single impedance having a real and an imaginary part, and that means that the node right here in the middle doesn't actually matter to us at all if we were going to apply a different circuit analysis technique. So now I'm going to put this in my calculator, and I encourage you guys to do the same so that you get experience doing this math in your calculator, because you're going to have to do it quite often. So 10 angle 30 times negative 1.5 I over 5 plus 4 I plus negative 1.5 I. And I will need to change the mode on my calculator in a moment. So I got 2.6 angle negative 86.565 degrees volts. It is customary to represent voltage and current phasors in polar form. So you don't have to by any stretch of the imagination, but it's probably a good idea to have your calculator set to give you a polar number as the default result of any complex math that you're doing. That'll just save you a little bit of time from having to go back through and do that conversion every single time, and really just convert to rectangular whenever you need it, which will be pretty infrequent. Okay. If you got a number that's different than this, first make sure that you convert your number into polar form, because I've definitely had students come up to me. I'm putting everything in my calculator the exact same way that you are, and I'm getting a different number. They're getting the rectangular form representation, which is going to look different, but it is literally identical. So if I'm giving you an answer that's in polar form, you need to compare apples to apples and look at the polar form representation. If your polar form number isn't correct, then we need to figure out where you've made a mistake. So, any question about the analysis that we have done here? Why doesn't the 3 minus J1 ohm impedance show up in our voltage division relationship? It's going to be zero, or the voltage drop across that part is going to be zero because it's not part of a closed current carrying path, right? So just because we're in the frequency domain doesn't mean the rules that we're used to don't still apply. All right. So now let's work the problem with the voltage source off and the current source on. So with the voltage source off, our voltage source is just a short circuit. We're still going to have our 5 and our J4 ohms like so. Here is our minus J 3/2 of an ohm capacitance. Let's call this VC double prime. Here's our 3 ohm resistor. Here is our minus J1 ohm capacitor. Here's our current source, 0. And I'm going to call this current here our phasor current IC, and I'm going to use current division to solve for this current, and then multiply that result by negative J 3/2 of an ohm, effectively applying Ohm's law in order to get the voltage that we're looking for. And because I'm lazy, I'm going to do it all in one step. So I can say that VC double prime is going to be 0.8 angle negative 30 degrees amps multiplied by negative J, 1 over negative J 3/2 of an ohm divided by 1 over negative J 3/2 of an ohm plus 1 over five plus J4. And I'm going to multiply this by negative J 3/2 of an ohm. And I can see actually that this guy and this guy cancel each other out. And so that's going to leave me with 0.8 angle negative 30 times 1 over minus 1.5i plus 1 over 5 plus 4i. I get 1.374 angle negative 107.905 degrees volts. Give you guys a moment to do that math, make sure you get the same thing. And just to be super clear, what I did here is simply me finding the current that I've labeled IC, and then I'm multiplying it by that impedance using Ohm's law to give me the voltage that I was looking for. So before we move on to our next step, anybody have any questions, comments, or concerns about what we did here? This is a review, so ask questions if it's not making sense. The whole point is that this doesn't make sense to some of you. All right, nobody's asking any questions. See. Exactly right. So our next step would be to apply the linearity principle of superposition, meaning that we can simply add our results together to get the result as if both sources were on in the frequency domain. 100% correct. So I have stored the results of both of these calculations in my calculator as variables X and Y respectively. By the way, it will be to your benefit to learn how to store stuff in your calculator. It'll make all of this way, way easier because of the amount of bookkeeping that's going on. So as Christina suggested, VC is simply the result of VC prime plus VC double prime, which for me is just X plus Y. And I get 3.995 with an angle of negative 93.758 degrees volts. Are we done? No. So let me explain why we're not done. My goal in this problem was to solve for the capacitor voltage in the time domain. We solve for the capacitor voltage in the frequency domain. Our last step is to convert back from the frequency domain into the time domain. How do we do that? Yeah, so we just put it back in the cosine form, right? So VC of t is going to be 3.995 minus 93.758 degrees volts. So the magnitude of our frequency domain response is the same as the magnitude of our time domain response. The phase angle of our frequency domain response is the same as the phase angle of our time domain response. We just put back in the cosine 2t stuff that we took out that allowed us to work in the frequency domain. All right, so working the problem in that particular way got us some experience doing superposition, as well as voltage division, as well as current division. Now I would like to work it an easier way. Okay. So I'm going to scroll up here and I'm going to make a copy of my original frequency domain circuit. I'll give you guys a moment to redraw this thing. Bless you. So we're treating everything now like an impedance, and impedances behave like resistors. But the impedance of our capacitor and our inductor are actually frequency dependent. Okay. That has some very special implications for certain types of circuits, particularly filters, which we're not going to really talk about formally in this class, but we can talk about things. So let me work this example problem, and then we'll talk about a filter just kind of as a way to help you wrap your head around this impedance thing. Okay. So we're going to work this problem a new way. I believe that I have told you all that your calculator is incapable of solving systems of equations containing complex numbers, and that is very true. That being said, for a circuit this simple, I can still apply nodal analysis, and I'm using quotes there because realistically, I'm just going to apply Kirchhoff's current law here to solve for the voltage that I want here in a single step. I'm just going to have to do some of the algebra that my calculator is incapable of doing in order to accomplish this. Okay. So what I'm going to do is I'm going to choose my bottom node as my reference, and this nodal voltage here is the V that I'm looking for. So if I were to write a Kirchhoff's current law expression, I would be adding this current plus this current plus this current together. Okay. So my current flowing to the left is just VC minus 10 angle 30 degrees volts divided by that total series impedance of 5 plus J4 ohms. Then I have my current flowing down, which is going to be VC divided by minus J 3/2 of an ohm. And then my current flowing to the right is going to be negative 0.8 angle negative 30 degrees amps. I'll set this equal to 0. Now, solving, I can see that I have a factor of VC that is being multiplied by 1 over 5 plus J4 of an ohm plus 1 over minus J 3/2 of an ohm. This will be equal to 10 angle 30 degrees volts over 5 plus J4, or 5 plus J4, plus 0.8 angle negative 30 degrees amps. I'm going to call this thing A, because that's what I'm going to store it in my calculator as. And this thing here as B. So A is just 1 over 5 plus 4i plus 1 over negative 1.5i. I get to be 0.582 with an angle of 77.905 degrees. B is 10 angle 30 over that same 5 plus J4 plus 0.8 angle negative 30 or 2.325 angle negative 15.85 degrees amps. And VC is just going to be what I have stored in my calculator as B divided by what I have stored in my calculator as A. And I get 3.995 angle negative 93.758 degrees volts. Scrolling up slightly, we see that we have the exact same magnitude and the exact same phase angle as before. So we got the same exact result a little bit faster or more efficiently. For this simple topology, this usually works. So the key here is effectively, let me scroll up to the original circuit, right? When using something like this, we need effectively a single node where we don't know the voltage, right? So I forced the circuit to behave that way by lumping these guys together as a single impedance. And these guys together as a single impedance through which I knew a current. But if this were a voltage source, I could have still done the exact same type of thing, right? So the only node that was an unknown quantity was this guy right here, which is what let me do it. Because I can solve a one equation, one unknown system using algebra all day long. It's not that hard. Once it gets to two equations, two unknowns, it's significantly more difficult to do using substitution and all of that kind of good stuff. And I would argue that you need to look for a different way to do it, right? But if you can describe the system as a single equation with one unknown, you can do stuff like this all day long. So did that answer your question or? Okay. All right, this is a quick aside thing, just because I want to talk about it. I'm not required by any stretch of the imagination to talk about it. But we're going to very, very briefly discuss a concept of a filter. Interesting stuff, at least to me. So let's say that we had a very simple circuit where we had a resistor and, just to make this very easy, an inductor, right? So this would be R and this would be L. In the frequency domain, we know that this impedance looks like J omega L. And let's call this our source voltage in the frequency domain. And let's call the voltage drop across our inductor our output voltage. This is a very simple voltage divider circuit where our output voltage would simply be Vs times j omega L over R plus j omega L. And we could define the transfer function of this circuit to be the ratio of the output voltage divided by whatever the input voltage is, which in this case would simply be j omega L over R plus j omega L. So the transfer function here is a complex number that depends on the frequency at which the circuit is operating. So what does this look like? What does this transfer function look like when omega is very, very small, meaning the circuit is close to operating at a DC steady state? So I would argue that it approaches zero, because as omega gets close to zero, we're going to have 0 over R, which is just 0, right? So for omega approaching 0, H of j omega approaches 0. So that means this particular circuit rejects very low frequency signals because the output voltage is 0. So whatever we apply at the input, practically none of it makes its way to the output. Now, instead, let's consider what happens when omega gets very, very large. Well, we would have j omega L divided by j omega L, essentially. So our transfer function approaches 1. So for very, very high frequencies, practically all of our input signal gets passed to the output. This is what we would call a high pass filter, right? And the reason that it works this way is because we're taking the voltage drop across an inductor, right? So we know fundamentally that at a DC circuit, an inductor looks like what? A short circuit. And the voltage drop across the short circuit is 0. What does the inductor look like at very high frequencies? An open circuit, right? So we're looking at the impedance here. So as j omega, or what does j omega L look like when omega gets really, really, really large? It looks like a huge resistance multiplied by j, right? So as omega trends towards infinity, it starts looking more and more and more like an open circuit, right? So that's the role that impedances play in circuits, right? So an inductor at very low frequencies looks like a short circuit. And then as the frequency increases, it gradually looks more and more and more like an open circuit. Capacitors work the exact opposite way, right? So we know that at DC, a capacitor looks like an open circuit. Let me write this out real quick, right? So ZC is equal to 1 over j omega C, right? So when omega is 0, we essentially have 1 over 0, which is infinitely large. Well, when omega is infinity, or we're operating at very, very high frequencies, we have 1 over infinity, which looks like a short circuit. So our inductor gradually goes from looking like an open circuit to looking like a short circuit, and we use that to make low pass filters because all of the low frequency components get passed. And then when we hit high frequencies, we start attenuating everything, right? Capacitor, yes. So this concept of impedances might seem a little weird because we're treating capacitors and inductors like they're resistors, and they are, but they're frequency dependent resistance. And we can exploit that frequency dependency and do some really, really interesting things, like pass and attenuate signals and all that kind of stuff. If we have both resistors, or excuse me, if we have both inductors and capacitors, we can make neat things like band stop filters and band pass filters and all of that kind of good stuff. And for those of you that go on into circuits 2 and so forth, we'll cover that in a whole heck of a lot more detail. But this is, to me, probably the most interesting application of steady state sinusoidal circuit theory, is it explains exactly how filters behave in a pretty simplistic manner. So anyway, that was a total aside, not remotely required in circuits 1 at all, but Christina made the unfortunate question of asking about impedance, and I'm a nerd. So yes. Sure. So really, we just need to look at what 1 over j is. So 1 over j, if I multiply this by j over j, I have j over j squared. Well, j is just j. What is j squared? -1. So 1 over j is the exact same thing as -j. Yep. All right. Let's see. So we've talked about superposition. We have done an example involving voltage division, current division. I've also shown you a little cheat code that you can apply KCL for certain simple topologies. What else do you guys want to talk about? Thevenin and Norton. All right. So trying to think of something gross but appropriate. Sure. Let me think of something here real quick. All right, so let's say that we have the following circuit, and I'm going to start in the frequency domain. So let's make this 20 angle 15 degrees volts. And let's make this 6 ohms minus J 2 ohms. J 4 ohms, 3 ohms, J 5 ohms, 10 ohms. J 9 ohms. Um, 1 ohm minus J 7 ohm. And let's make this 2 angle 0 degrees amps, like so. excuse me, and let's say that we were interested in finding the current flowing through this indictment, right? So I've tried to make a circuit here such that we can't just use that KVL trick I used earlier, right? Because there's definitely at least two nodes in this circuit that we don't know the nodal voltage of, and I'm too lazy to solve a two equation, two unknown system by hand in order to do nodal analysis for this. Mesh analysis, it seems pretty obvious that this would be four equations, four unknowns. There's no way in hell I'm doing that by hand. So I've got to figure out something else to do. Okay. So what I am going to do is I am going to use Thevenin and Norton's theorem to simplify this circuit into something that's a little bit more digestible for me to analyze. Okay. So I'm drawing this dashed orange line right here. And what I'm going to do is I'm going to disconnect everything to the left of this dashed orange line and replace it with its Norton equivalent circuit. And you'll see why I'm choosing to do the Norton equivalent circuit in just a moment, okay? So when I disconnect that bit, I'm going to have 20 angle 15 degrees volts. Six minus J2, J4, 3 ohms, J5 ohms, 10 ohms, and there's my set of terminals. So my question to you guys is, would it be easier to solve for the Thevenin voltage or for the Norton current here? I personally think it would be easier to solve for the Thevenin voltage here. That being said, if we did a source transformation, it would be very easy to solve for the Norton current. But that just adds a step that I don't necessarily need, okay? So I'm going to solve for the Thevenin voltage. So the Thevenin voltage, VTH, how would I solve for that? Right, but how? Yes, voltage division. Okay. So this to me looks like 20 angle 15 degrees volts. In my numerator, I'm going to have 3 plus J4 ohms. In my denominator, I'm going to have 6 minus J2 ohms plus 3 plus J4 ohms. And I'm going to throw this into my calculator. So I get 20 angle 15 times 3 plus 4i over 6 minus 2i plus 3 plus 4i, close my parentheses, and I got 10.847 with an angle of 55.601 degrees. Volts. I'm storing that as X for what it's worth. To find my Thevenin impedance, I'm just going to turn off my voltage source and look into the terminals of my dead network. Excuse me, that should be minus J2 ohms. So looking in here, I see 10 plus J5 ohms plus the parallel combination of 3 plus J4 times 6 minus J2 over 3 plus J4 plus 6 minus J2. Which I get to be 14.603 with an angle of 25.532 degrees ohms. My Norton current is just going to be VTH divided by ZTH. Or in my calculator, that's just X over Y because of how I stored things. So 0.743 with an angle of 30.068 degrees. Amps. And I'm storing that as Z for what it's worth. So the reason why I chose to break my circuit up there is I can replace everything to the left of that dashed orange line with my Norton equivalent circuit. So I would now have I Norton in parallel with Z Thevenin, where I'm just using this box as a generic two-terminal element. Here, just representing whatever my Thevenin impedance is. And then I'm going to connect to those terminals the remainder of my network, which I have to scroll up here to find out what it was. So a J9 ohm inductor. Through which I'm trying to find IL, if I'm not mistaken. One minus J7. And then 2 angle 0 blowing up. And since I've replaced everything to the left with my Norton equivalent circuit, I now have a circuit that I can literally just use current division to find the thing that I'm interested in, right? So my current IL would be I Norton plus 2 angle 0 degrees amps times 1 over J9 ohms, 1 over Z Thevenin, plus 1 over J9, plus 1 over 1 minus J7 ohms. So throwing this into my calculator, I'm going to have Z plus 2 times 1 over 9I divided by 1 over ZTH, which I stored as Y, plus 1 over 9I plus 1 over 1 minus 7I. I get 3.625. Angle negative 81.544. Degrees amps. So we took a big ugly thing that looked like we were going to have to apply either nodal analysis or mesh analysis and broke it down into more manageable parts using Thevenin and Norton's theorem. So if we can make a part of the circuit look like a two-terminal network, we can replace that part of the circuit with its Thevenin equivalent circuit if that makes things easier, or its Norton equivalent circuit if that makes things easier. In this particular case, the Norton circuit made things easier. Right? So instead of using Thevenin and Norton analysis as just an abstract thing, we're now bringing it into the fold as a tool to simplify a complex circuit into something that's a little bit more manageable. Isaiah. It is, but we are working in the frequency domain. So everything that we did, like we are saying, we didn't really care what the time domain representation was. We just started in the frequency domain, so we didn't have to convert things over. So that 2 angle 0 just means that we had 2 cosine some angular frequency that we were never told t plus a phase angle of 0 degrees. It's still very much a sinusoidal circuit. Yeah. So you are 100% correct that rounding error can compound very, very easily when analyzing these circuits, which is why I very much make it a point to store stuff in my calculator at every conceivable step. And I would highly encourage you guys to do it as well. If you need any help figuring out how to store things in your calculator, I would be more than happy to do so, or happy to explain it to you. What else do we want to talk about for today? Your calculator can't handle complex numbers in its system solver.
So you want to break it down to, if you do know, you break it down to where you substitute.
Yeah. There's nothing stopping you or anyone from using techniques like Kramer's rule to manually set up your matrices in order to handle the complex numbers. But to me, that takes longer than it did to just break this into something more manageable. So I've definitely seen students do that. That's entirely up to them. That is the issue. Yes, there are tons of calculators that can do it. None of them are FE approved. Yeah. Your TI 89s, 83s, 81s, 92s, etc. can all do it. I'm sure there's fancier Casios I'm not aware of, but they're not allowed to use them. Yes. ncees.org. You can file your complaint there. Yes, Walker. Yeah, so polar form is usually used to represent voltages and currents, so that's what I have my calculator set for default in. Impedance, I would argue, is more typically expressed in rectangular form, but you'll still see it in polar form as well. And so because we're usually solving for voltages and currents more so than we are solving for impedances, I tend to leave my calculator set in polar form as the default. Your calculator does not care. It can add, subtract, multiply, divide, any combination of polar and rectangular stuff. But yeah, I don't want to spend the extra time of, all right, I got a rectangular number. Now let me go ahead and convert it. Just let the calculator do that by default. Anything else? Since I'm done with the lecture part of this thing, if you guys want to work on the in-class assignment and all that kind of stuff, that's groovy. And if you have any questions about anything, please let me know. All right, multiple people are asking about homework set number 19, problem 3. So I'm just gonna let you guys know how I would approach this. Christina, rattle off your information for me, please, ma'am. Walker, rattle off your information for me, please, sir. All right, so 0 and increasing at t is equal to what? 10.1 milliseconds. All right. Here, and I'm going to go ahead and possibly pre-apologize because looking at the time difference between these two things, it looks like you might be an unelected soul, but we'll figure it out. Okay. So we're told specifically that we have a sine function that is 0 and increasing at t is equal to 10.1 milliseconds. So I'm going to draw a plot here. As per usual, because I can't draw, it will be pretty crappy, but we'll make it work. Yeah. So this is time, and this is our function. Let's just call it f of t for a lack of a better thing, okay? So we're told that at 10.1 milliseconds, our function is 0 and increasing. And then over here at 12.5 milliseconds, it hits its maximum value. What was that maximum value? 11. Yep. So what was mathematically described to you was exactly 1/4 of a cycle of a sinusoidal wave. So this time to this time is t over 4, okay? So you can use that piece of information to calculate your angular frequency omega, right? So omega is equal to 2 pi over capital T, and you have enough information to solve for capital T. The magnitude of your function, so let's call that f sub m, is just that maximum value of 11. Okay. And this distance, delta t, is related to your phase angle, right? So your phase angle will be, let's see, so I have delta t, so that's measured in seconds. So let me think about this. So omega, radians per second, times delta t, measured in seconds, gives us an angle in radians. The phase angle is going to be a negative quantity because we are shifted to the right. And because we want our phase angle to be expressed in degrees, I'm going to multiply this by 180 degrees over pi. Were you told that you want for the first part, I think you're told that you want the phase angle to be a positive quantity as well, which means I'm going to add 360 degrees to it. And so those pieces of information can be cobbled together to get you your sinusoidal waveform that would be of the form f sub m cosine omega t plus some phase angle. Sorry, it's explicitly asked you for a sine function first. Like that. So it tells you specifically that the function was 0 and increasing at a specific time, which tells you that you're looking at a sine wave because sine is 0 and increasing when it starts its cycle. Yeah. If it said it was at its maximum and decreasing at a particular time, then you would know that you were dealing with a cosine function. Well, but very specifically, if you plot things out, you can see that it's okay. Walker, my concern for you is that let me think about what the period is here. So your particular signal actually goes through a full cycle during this delta t thing here, because you have a poor set of numbers. Because the period that I get is 9.6, which means that, let's see. It's 10.1 minus 9.6. Over here at positive 0.5 is where one full cycle starts. And so you're going to have like an aggressively large phase angle, like you might have to add 360 because of where yours started from.